Imagine you are the person who wants to install the updates, hotfixes released on the tools you used in the org you work on a large scale, and you take more responsibility in doing that. I mean, the story we are going to talk here is about a software update, particularly a hotfix. But this time, the hotfix is signed with a legitimate certificate. But still, you are the nerdy guy in your team who still wants to check this particular hotfix. You drop it in your sandbox or in Virus Total or to check on suspicious markings on the file. And you're so happy to see that kit comes clean. So you're happy to, on your day's work, to install those updates on a large scale. But on the other hand, we never think about the invisible stuff that's happening in the background on the software supply side. It's kind of trust relationship we have, assuming they also follow proper OPSEC. But even weeks or months later, you read about this in this news that these so-called updates that you trusted, verified, and installed in your environment is the reason for a global cyber hack, which includes the organization you work as well, which we call as a supply chain compromise. You might be even be thinking, man, I was responsible to act immediately, but suddenly that act has made a U-turn. Hmm. Pretty much not the case because we always trust the things we see and we apply because we trust the supplier, but it always ends up in the other way. If you are one of the guy who has been part of this and you are now trying to read all the threat research articles, checking those IOCs running to a threat intel team without even deeply checking what has happened behind this signed DLL which has been backdoored, you are the right place to check it. This is Intel Archives. We are going to see about the SolarWinds SUNBURST analysis here. I mean, on the other hand, the attacker, whomever who has planned or were part of it, depending upon the scale of the compromise, you could really see that the recon they have made is simply mind blowing. I would say. The one other point we can point out is that the coding conventions they followed is so impressive because even most people, even the people who work in SolarWinds, even they would have believed that this code was developed by one among their internal employees. I would say so clean, so legitimate. I would say the same coding conventions they have followed, which also gives you the suspicion that the attacker himself would have controlled this the the backdoor at the source code level itself. I mean, no matter how perfect the method they do, it always leaves some traces. I mean, these inevitable traces constitute the threat intelligence base that works on the defensive side. I mean, this threat intelligence basis is where the defensive side itself, I would say. But no matter what was said, we still need to accept that this operation was super planned and very stealthy in its lead. Before driving into this technical aspect, I mean, looking into the DLL code itself, let me quickly walk through the stages of the attack that was in the news. So let's have a quick look on the Sunburst attack chain. So I took this illustration from Symantec since it was quite handy, I would say. Uh, so the Trojanized SolarWinds was being delivered from this official hotfix site, SolarWinds hotfix site, which is the downloads.solarwinds.com. So we we mostly knew that it was this SolarWinds core version 2019 hotfix, but there was also many tweets from the infosec community that it was also present in another hotfix package, which was 20161 core installer.msa. Both these hotfix packages had this compromised onion core business layer.dll, which is nothing but which has that sunburst backdoor in it. Moving on, as you would have read in most threat research blogs, you knew that it waits for 12 to 14 days before execution. It does many things actually, I would say. It tries to disable AV and EDR. It tries to check a list of drivers. It has blacklisted services which it checks like kind of anti-forensic, anti-reverse engineering tools. Um, it, it has a clean DGA algorithm implemented, which reads the domain name, the MAC address, as well as the GUID of the machine, which has been passed to a nice implemented DGA, which then generates a domain name which needs to be checked from our environment. So pretty much a lot of things, and also finally it opens a backdoor which brings in the second stage payload, which is the teardrop. So the sunburst, the compromised the backdoor DLL has a HTTP backdoor code implemented, which then brings in a teardrop backdoor, which actually executes in memory, pretty much not touching the disk. And according to Symantec, they say that there have been two versions they have seen in their research. Both were trying to read some kind of a configuration from a JPG file, and then it extracts some embedded code which has a copy of a Cobalt Strike beacon, which additionally performs lateral movement, etc. But in the stage, I really want to question myself that why they want to drop Cobalt Strike. I mean, they could directly drop the ransomware here, but it's pretty much a surprise for me because they chose to drop Cobalt Strike beacon here instead of some customized payload or even ransomware. But that's how it is, I would say. So this Cobalt Strike beacon, I would say that it's contacting some CNC. It tries to steal credentials. It pretty much does the things which a threat actor would do. Who compromises a big company? They want to have a persistent access to the assets of a big company. They want to compromise. So in the next section, we will be having a detailed analysis of the Sunburst backdoor itself, the Trojanized SolarWinds on-air layer.dll. So this is the SolarWinds hotfix, which is of analysis now. Let's right click, extract, open. So there are a lot of DLLs inside in this hotfix. The one is of interest is the business layer, Onion Core business layer. Let's open this DNSpy. Let's drag it up here. It's going to be inside business layer again. Again, it's going to be the same name actually. So this is where the backdoor code has been inserted. So before jumping into the analysis, there are two things which I would like to say to inform in the beginning. Is that when you try to analyze this code, that you will be seeing two uh, kind of obfuscation, I can say, is you will be seeing this kind of hashes. I would say a lot of hashes inside this. Just they want to keep under the radar to make analysis different. And the second thing is there's gonna be a kind of obfuscation in kind of base64. If you come down, there is gonna be a lot of obfuscation. Again, trying to make the analysis a bit difficult and to be under the radar. So there are two ways to first clear up this base64 obfuscation. One is to use CyberChef directly, or the other way is to use de4 dot. Let's first use CyberChef, I would say. Let's copy this one, which is gonna be coffee. Let's go back. I'll copy this one, and since it's in the base64, we have to decode it from base64, which is there. And as they have used the deflate function, we have to do the inverse actually, which is the raw inflate. If you do it, you can see it's pretty much in clear text now, which is readable. So they are trying to make some WMI query, which okay. Actually do this for the entire code using CyberChef, or we can pretty much do de4 dot. The way to do it is that you need to go to this unzip function, click on the unzip, and copy the token which has been specified here. Right click, copy, and let's close, which is not very important. And let's go to de4 dot, d.for SolarWinds, and then the command I have already done was actually this one, which is actually this. This is what I copied there. Let's paste this. Let's remove the 0 and X, which is not required. And let's copy this one. So it's going to be -str type, delegate -str talk, and the token number which you have obtained from the unzip function. Let's just press enter. Let's do all the magic for us. And you see, it has cleaned it and stored in the same place as SolarWinds Onion Core Business Layer clean.dll. Let's close this one. Let's go to d.fort inside this path. It's here. Now we can go to DNSpy. Let's drag in the cleaned one now, which is this. Let's go back again, the same place, business layer, which is gonna be the onion improvement business layer. And let's scroll down quickly. And you see, now everything has been cleared up. You see here, you can read the Deobfuscated format here, which is in clear text. I mean, it's pretty much every part of the code is now cleaned. But the hashing part, which I explained, cannot be directly cleaned. But again, thanks to the FireEye research, I would say, I will just show you the one example. If you see here, there is a couple of hashes here. Let's just right click, copy it, and go to the GitHub page from FireEye. If you go here, they have done some hashing here. If you click on the hash, just copy it, Control X, and you can see, you can find the related hashing function, which is nothing but SolarWinds business layer host. The hash format they have followed here is going to be the FNV1A 64-bit hashing, which is nothing but a Fowler no vwall hash function. Frankly, I had no idea until I read this code. So thanks to the amazing research from FireEye. So now we have the clean code. So just let's go inside SolarWinds business layer, onion improvement business layer. Let's check once it's been cleaned to see. And yes, it's clean. So the first step to check the function is the interesting one is the initialize function. Let's go to the initialize function. This is where the code initializes itself. To check from where it's been called, let's do the analyze one. And pretty much you can see it's been used by the refresh terminal. It's just one function which is being used by it. Let's click this one to see. And we can see that the refresh terminal is the function which invokes the initialize function. And it's a nice sneaky way to bring in the code insert into the refresh terminal, because it's not the conventional way of calling the function, because it's been called from the SolarWinds business development class. If you see here, yeah, so I mean, so the SolarWinds background inventory, business layer background inventory, and it has this refresh terminal. So let's check, and if you see, there is an interesting if condition. It makes sure it's alive every time. I mean, this is the best way to call the function, because it ensures it's been persistent, and every time it is alive. If you click this is alive, there is an is alive lock being created, which is has if else loop itself. So that means it makes sure there is only one instance of it's running, and it's been called up again and again. Pretty sneaky, I would say. Let's go up to the initialize again, which we can go again from here. Let's close up this one, and to check, there is the first function is it tries to get the current process, and it obtains the hash of it. So it tries to read some process name, which is again being hashed in some format. Let's copy this one. Let's remove the URL, and pretty much we can see that it matches SolarWinds business layer host, which confirms to us that this hotfix wants to run only in the environment of Solar Business Layer host.exe. So it tries to blend in within the original function so that it gets undetected every time. Let's go back. It tries to check whether it's runs on the SolarWinds business layer host.exe, obtains the correct process and the hash. Again, if you see here, if it's all if and there is no else here. So even if any one of this condition fails, the malware does nothing. It's pretty much you develop a malware and you make when you have so many checks. And the end, if even one fails, it's in dormant position. It just stays there doing nothing. And if this passes, it tries to obtain some kind of last write timer. So it tries to check some dormant time, I would say, which has been done in hours here. 288 hours, it's going to be 12, and 336 is going to be 14. So it tries to check between 12 and 14 days of dormant period. That is the last write file. And if it is true, it wakes up slowly. And then it tries to create a named pipe stream, obtaining an app ID, which is the process GUID, which has been mentioned here. Again, it makes sure that it wants to run only one instance of it. That's why it tries to create a name pipe stream here. And pretty much interesting thing I would say that big name pipe stream, it's a nice way to hunt as well, because this name pipe stream can be hunted with sysmon event id 17 and 18, I would say. Pretty much if you see that sysmon an example of a sysmon 17 event, I would say we can see here that the task category is pipe created, pipe event. You can see the GUID which is here. So pretty much that is what they were trying to do. And it was also confirmed from FireEye's, I'm sorry, from McAfee's research. Uh, I had it open somewhere. Yeah, exactly. Yeah, you see, the victim is not in the block list. The sample will create a name pipe to instance that one instance of the backdoor is running. And this is the instance of running backdoor. Pretty much it reminds us to the fact that collecting sysmon logs in the centrally located CM helps a lot in hunting, I would say. Let's go back to the code again. So it tries to check, and then there is a nice function which is the read report status. That means it tries to obtain some status here. Let's click on the status. I'm sorry. Let's click on read report status, which again obtains the status, which again reads config from some kind of, what is this read config? It tries to read a config, which is actually try parses it. Okay, status name. Yeah, the config has been read from the report watcher entry and report watcher postponer. So it seems that it's, to what I can understand, it's seems to be the configuration option was been maliciously reused, to what I can see, because it has been called already. Let's go back, and it reads three new status, which is going to be case 3, 4, and 5, which is going to be truncate, new, and append. Pretty much, if it truncates, the malware resides there and does nothing. As in the FireEye report, they were saying that it's at the mercy of the attacker. Either he wants to do something, or the target is not juicy for him, so he tries to truncate itself and let the malware be dormant for there, doing nothing. Or if in the other case, if it is not a truncate, let's assume that it's not a truncate here to make the code run further. It tries to not a truncate, then it starts obtaining the domain name. I mean the Windows domain name using the global IP properties function. And once it does, it tries to make sure the domain name which it has obtained is being passed to a series of not if loop, not condition with an if loop, which is going to be null or invalid name. So it tries to check whether the domain name against some kind of invalid or null name. Let's click this one, which goes inside again. It tries to obtain the domain, which is a if loop, which comes again, and it tries to obtain some hash on some pattern hashes on a for loop. Let's check what's this pattern hash here. Again, this it has been hashed up with the algorithm which we saw, which is what? Let's try to copy again this one. Seems to be it doesn't like these things. Let's go to the FireEye stuff. Let's put it up here. Pretty much it tries to check this domain name against a predefined block list or blacklist, I would say, which has some kind of SW dev local. So it tries to, I assume that it's gonna be the SolarWinds dev local environment. And thanks to again the community, I would say that this is the complete cracked version of the code. So it tries to check again on SolarWinds dev.local, local lab, it SolarWinds North America office, emia.sales, dev.local. So it doesn't want to infect the dev environment of SolarWinds. Maybe the attacker had complete control of the source code behind. Maybe, let's not be too judgmental on this, but it tries to see if it is not present in one of it, then the code passes off. Let's minimize this. It's not present in one of this blacklist. Let's go back, and this pattern hashes has been obtained from kind of a pattern list, which is nothing but a kind of regex, which tries to blend in SolarWinds inside. So that's how the pattern hashes has been formed. Let's again go back. If this has been done, then it tries to obtain the user ID of the machine itself using the get or create user ID. Seems to be kind of a nice footprint, I would say, a recon, I would say, of the machine itself, because it tries to read the device info here. Let's click. That's not device info, which obtains the domain name plus the machine GUID from this registry path, and it has its own XOR implementation here. Tries to obtain the MD5. It obtains this value and takes this MD5 of this GUID plus domain, as well as the MAC, I would say, because you see it tries to get the network interfaces here as well. That is something interesting, I would say, because you see the read device info goes to this function which calls up, which acts as get all network user interfaces on the device info here, which is actually tries to get the interface, I mean the MAC address of the interface using the get physical address function and the domain plus the machine GUID. So it tries to obtain all this three values. It obtains the MD5 hash of it, and it has a custom XOR implementation which is encoded with some substitution value, I would say. Kind of a sneaky implementation of computing the hash. So, so this part is actually, I think it's where the DGA implementation comes into play. So let's keep this aside in the fridge for some time, and let's come back to the original code. Assuming that every function here has passed, this function has passed, and the status has been read as not truncate, then the update function is called. I mean, the update function is where everything has been done with the backdoor, all kind of the dirty stuff has been done, I could say, or it's the function, I would say. Let's click the update function, and immediately you can see the update is being given inside another if condition which checks on update notification, and it has a while loop which calls inside a track process. That means this function is given with a not value. So this has to be false for this one to execute. If this is true, nothing happens again, because the bad code is actually within this while loop, I would say. So the update function calls update, and the update notification uses this track process itself. And if you see within the update, it has two important other implementation of class. One is the crypto helper, which actually obtains the user ID and domain. So this we can confirm that this is the helper function which is used to generate the DGA, I would say. And pretty much the HTTP helper, since I already analyzed the code, I can clearly say that HTTP helper function is the backdoor, is where it is been implemented clearly. So let's go down to update. Before going to update, let's check what's there in update notification, because the track process has been used. Let's see some notification, and let's see what's there is in the track process. If you see the track process, it tries to obtain some assemblies. It has three functions because it obtains the process here an array, and it tries to check search assemblies which should return true, and it also tries to return some search services and search configuration. If this returns true, that means that there is some kind of blacklist implementation has been done. So if one of the blacklist, if one of those things which is it is trying to search within it returns true, the malware exists itself. Huh? So pretty much it is making some checks here, and it wants to return it to false for the code to continue. So let's check what is search assemblies here, which again goes inside process, which is a for loop. It opens a get hash, a process name, very good, and it has some assemblies timestamps. Let's click. Ooh, it has a long list of hashes. Huh? Again, as I told you, you can just copy these hashes and go to the FireEye GitHub page to compare, or to see what is it. Here the same thing has been done. Let's see what this hashes is been all about. Boom, it's here. The assembly timestamps is nothing but the hashes results to some kind of a anti-tampering checks, or I would say some anti-forensic checks, because it has blacklisted all these tools inside these hashes. That means if any one of this tool is been present, the malware exits itself. It checks a long list, I would say. You see, there is autopsy, which is for forensics. There is binary ninja, D for DNSpy, which you're using, fake DNS, PEC, Visa. There was also sysmon, procdom, sysinternals, radar 2, and pretty much win debug, everything, some forensics tools, everything has been in the blacklist. If the malware finds this hash, this condition is going to be true, it exits. It's a long list of checks, frankly, I would say. So let's go back, and it doesn't stop from here, because it tries to check again. It tries to make sure there is some search services, which is also trying to check. Let's see, it's trying to track from search services. Let's go up search services. It again obtains the hash with the process name. That means it doesn't like something which has a service list here. What is it? So there is some kind of another list or a big set of implementation has been done here. So let's go back to the code which has this comments for us. Yeah, which is gonna be this part, I would say. Sorry. So you see this list, which is the service modified lock, which is exactly, I can show you back the service modified lock and service configuration. So this is the list actually. It tries to make sure, it checks that these have been it tries to make sure these services have been running. I mean, it makes an extensive check, I can say, of what's the EDR which has been running in the environment. That is an AV on EDR. You see that this is going to be Windows Defender. It tries to check for Windows Defender AP, some MS Azure ATP, Carbon Black. If you come down, CS Falcon, CrowdStrike, Falcon Service Agent, FireEye EDR, XAGT, FireEye EDR, ESET EDR. Also, there should be Kaspersky for sure. I saw it somewhere in the middle. FSecure. So that's going to be a long list of checks which is making to check the process, or the AV or the EDR it wants to track. Pretty impressive, I would say. Sorry. Let's go back. And once it finds the relevant stuff which is running, let's see what it does. It tries to run, and what it says is that if one of it is not disabled, it wants to disable it using the manual mode. Let's check what the set manual mode does. Pretty much interesting. It tries to obtain the registry key of the service, and it wants to set it to value of 4. So that means it's like it ensures that this none of the EDR and the AV is getting this backdoor stopped. So it wants to disable it so that it can run smoothly in an environment. We can also so you see the number of 4 value is to disable it. So it's trying to make sure it's been disabled. That's why. So that is going to be 0, 1, 2, 3, 4, and 5. So it tries to set it for 4, which we saw in the code here. But 4, and it makes sure it's been disabled before it can do whatever it wants. Pretty impressive. Let's go back again. So this has been done, this has been traversed, etc. So if everything goes good, it has some additional searches as well now, because you see it tries to still process track on some search configurations. Let's see what is search configuration, which has some kind of object search. It has a WMI query because it wants to search the Win32 system driver. It also wants to know what driver it runs. I don't know why it wants to know the driver, but it tries to, which is in the config timestamps, I think. Yeah, just obtaining the driver. So let's go back again. What is it? It's gonna be, let's copy this one. So it's easy for us to search. Copy. Yeah. So it tries to look for the system drivers as well, which is gonna be, what is it? It wants looking for logarithm, Bromium, Cyber Reason, Dell SecureWorks, Sentinel-1, Alteris, Symantec EDR. It also checks the system drivers as well. Back again. If everything goes good, I mean, what to say? If no services, if the process, service, and driver checks passes, it needs to pass all these three checks. The process is nothing but the blacklisted data process should not be present. The services which it wants to disable, it needs to be disabled, and as well as the driver checks, it has to pass. If everything goes good, it doesn't stop here actually. It again makes sure there is another if loop which checks the server connection, which goes to something called as API host. That means it tries to resolve to check it's reaching somewhere. Nice. So it tries to check it's able to resolve this api.solarwinds.com to start the next stage. The remaining part of the code has been executed. Pretty much a lot of checks, I would say. If you come down, you can again check that. Let's check the service that it tries to track the record, something blah blah blah. Some kind of crypto helper. It tries to check the get previous string. Let's see what is get previous string here. I think this is where the DNS query has been formed, because you see the crypto helper function has been called here, which has some kind of checks being done here. You see it tries to obtain a if loop, blah blah blah. So what is the text? It's been stored here. It tries to obtain the create string using the get status, but that's not sure. Interesting. What is a secure create string? It's trying to do some base 64 encoding and stuff before that. So let's go back again. It tries to obtain the report status, which is the crypto function. I think if we go to the crypto function, it will be a bit more clear, I would say. If you see that we just saw this update notification, what it was trying to check the same thing, but either of the same logic has been implemented here as well. Now, if this one fails, I mean, again, it's gonna go to the while loop here, which again does the same thing. It obtains the get process, search assemblies, search surfaces, and search configuration. Again, it resolves. If this checks goes good, it's going to come to the next stage, which calls up the crypto helper function. I mean, the crypto helper function is where the DGA has been formed. Let's go inside the get previous string. I mean, everything will have the same implementation to what I saw. So it stores as text. That means this is where everything has been, the result has been stored. So let's go into the crypto alpha function itself, which gets the GUID, which we know the string actually, and it tries to call in a function called decrypt short, which is nothing but it tries to check that the domain name obtained matches this kind of characters and pattern. If this one goes good, it tries to call some base64 decode on encode. I mean, why it has to decode here? It just needs to encode for me. Okay, just some they play with names actually, because you see base64 decode as in turn calls a function which creates the DJ algorithm, which builds up the DJ algorithm here. If one of it matches, it tries to call the base64 decode. I mean, it has to be encode here, but just for some naming conventions they play, I think pretty cheeky, I would say, which tries to build the which tries to generate the domain name, which this class is initiated from the 8-bit user ID, which we already saw in the beginning, and the computer name and the substitution value. The substitution value is actually this to build the domain name, I'd say. So if this goes good, this comes back here, it again obtains the get status, which is back here. I would say the decrypt shot. Let's go back, crypto helper. So this is a function we saw, and let's come back. The result has been stored in this text, which is the result, which is nothing but the get status. So the get status here is gonna be where the domain has been formed. So what is it? Let's check what is domain 2, which is num per appsync.api, which you would be knowing. And domain 3, what is it? Which is going to be either one of this, EU West hyphen EU West or East, one or two, and which is going to be the domain 1, which is actually the base domain, asvm.cloud. So that's how the DJ has been generated, I would say. So pretty much if you go and cross check what FireEye was saying here, you see this is where we saw this is where the base domain, and we already saw that it's going to be either EU West 2 or 1, and it's going to be an AppSync. So pretty much if you go back sorry, to the code itself, the domain 2 will be appsync.api, which is this. Domain 3 will be either one of this, which is going to be EU West, EU East 1, and what else? I'll go back here again. Again, I'll go back, not here, sorry, it should be here only. And domain 1, which is going to be the avsm.cloud. Yeah, avsm.cloud, which is going to be this. So this thing has been generated, and whatever we generate with using this crypto alpha function, the decrypt shot, whatever it is passing, which generates the the domain with the parameters which has been read from the user's environment itself, which is nothing but which we already saw here. I can go back if you want to get revised here. Let's go to initialize quickly here. That will be easy. Global IP properties is create as UID. This is where I would say it tries to read the device info using the network interface. That means it obtains the MAC address, the Windows domain name, plus the user UID. Create user ID by reading the device info, which is nothing but obtained from the reg key. All these three things have been they take all these three parameters to obtain the MD5, and a custom XOR implementation has been done to obtain the 8-bit user ID, which is being passed to what the next function we have seen. We ran through DGA to obtain a new hard-coded new DGA, which has been hard-coded to the domain information that has been already appended. Let's go back to the update from where we left. So this is where we saw this has been done. So that means that it tries to also read the address family. This is the address family. I think it tries to obtain the IP address info. Yeah, it also obtains the canonical name. It tries to make sure the canonical name is also not empty. Before that, it tries to go inside the DNS records. Okay, good. Just not empty. And if everything goes good, and if the status is actually not drunk yet, it tries to call the HTTP helper class, which is actually the backdoor, the which is the class which implements the backdoor functionality. So you see, it tries to initialize the HTTP helper here. So this is where the HTTP helper has been initialized. The moment you see that it tries to, so job engine, which is where the parent class has been done. Can we go inside job engine? So if you say inside the job engine, which it tries to execute a lot of stuff, the jobs which is the backdoor it's gonna do, it's gonna set itself to idle, exit. It tries to obtain the system description. It wants to upload system description, process description. It even kills task. It writes file. This is where the second stage payload has been done, which according to the research published by FireEye and Microsoft should be the teardrop payload. It tries to check some file hash. It modifies the registry value. It even reboots if it wants some. Impressive. Yeah. So it creates the upload request, and it tries to gets a lot of parameters to upload the status code, I think. Yeah, it's uploading the status code to make sure everything is reachable. And it also tries to read the registry value, which we just saw. And if you come down, it also obtains a system description, I think, somewhere. Parse service response. It's trying to parse the service response. Implementation. Create upload request. This is where it tries to make sure it reads what else it reads. It reads a user ID, it obtains a session ID. Then what it does, it wants to have the event type, which is Orion, event name, duration. It tries to convert them to base 64 in a JSON format, and it invokes the HTTP post, the HTTP content type, to upload it back up to the server, which exactly matches to what FireEye actually says here. I mean, we are trying to compare and contrast. I mean, that's nothing cutting edge research we are doing here. The only thing we can do is that we can always compare and contrast to what they have said. It's a very good learning for us. I mean, we don't work in FireEye, so I mean, this is what we can do, frankly. So this is what we actually saw from here. If you go back to this one, the jobs engine actually. If you go back, tries to initialize this one, the jobs engine here. So we can see that idle exit set time collect system description, which is what we actually saw here actually. Let's go back, let's come down. It tries to does the create upload request, which is actually this. It tries to read the user ID, the session ID here. It tries to event name, which is going to be Orion, event manager. It tries to check. It also makes sure it's true. It makes the content type should be in JSON, and the web request should have this content type, which pretty much matches to the screenshot which FireEye has put here. So a unique ID file for the victim machine stores a random GUID HTTP thread, blah blah blah. So everything has been compared and contrasted here, I would say. So base URI implementation. Let's see what is it. Tries to obtain the user agent. It tries to check the server connection again. The IP host entry, get address family, base 64 encode, pretty much the same thing. There should be these jobs here. If we go down here, so we just saw just the upload system information, which is just we just saw here. What's more interesting is that it's the run task and the write file is the most interesting thing. We already saw that write file within the jobs, which is gonna be where it reads the second stage backdoor using this file stream. Function is the run task. It makes sure whatever it has been run the second stage backdoor or the second stage payload, it makes sure it tries to execute inside using the usual shell executor. Pretty much impressive one. If you again go back to initialize again, initialize, let's again go back to update. It's nice to go back up and down, frankly to say. So much interesting. Initialize, it's where it's been done. The job engine we saw, it tries to create the upload request. Make sure delay is 1 minute. Execute engine. It even tries to reboot the computer here. The execute engine, it tries to read the, it tries to obtain the collect system in description. Upload system description. Yeah, you see here run task. This is where the run task has been called here. It has been in case actually. So I'm sorry. The run task has been invoked here, and the write file has been invoked here. So this is where the separate function which we saw a few minutes before has been called. It made sure the write file function is called to obtain the second stage payload, and the run task makes sure it actually executes it. Sorry, it's here. This is the where. It tries to execute a user function. I mean the HTTP helper class which we just saw, this class, I can go back again. To go back again is to start from the beginning because that's more easy than traversing this code, frankly to say. HTTP helper initialize is where the backdoor has been implemented clearly. We can recap to see how much checks it makes, frankly to say. Let's go back again to initialize. You see, it tries to make sure it runs in SolarWinds business layer host.exe. If yes, then it tries to check the dormant install time, the last installed write time. So it should be between 12 to 14 days. Then it's true. It again comes back. It tries to read the status. It has to be in three status, which it reads either it's to be new, append, or truncate. Depending upon the result, it comes back. It tries to read the system information using the global IP properties. Also, it obtains the domain name and it makes sure the domain name is actually not present in one of those dev environments, which is SolarWinds dev.local. If that is also not there, then it tries to make sure obtain the system information, reconnaissance within the machine. It obtains, you see, it obtains the physical address, the domain, the physical address, as well as the GUI of the machine, MD5s it, XORs it, and has the 8-bit value. If everything goes on good, the main function which does all the dirty work is the update one. It tries to call the update one, which again has another if condition with an update notification, which does the same kind of checks, which is the track process twice to make sure if either one of it falls, the rest of the code executes. Inside the track process, if you go, it has again make sure it tries to have a search assemblies, which is nothing but a long list of blacklisted stuff, which has the anti-forensic, anti-RE checks, sysinternals, etc. If that is present, the malware exists. If not, it comes back again on search services. I would say it makes sure it it makes sure it tries to tracks the services which has been running, which is nothing but the EDR and the AV which is running within the machine, which is actually being listed here, which is where we saw it as Windows Defender, Azure ATP, Carbon Black, Kaspersky, CrowdStrike, etc. If those things are being there, it makes sure it invokes a set manual mode function. Click here. It reads the registry service. It wants to set it to back to 4 in manual mode. Make sure nothing runs so that it can do whatever you want. If this thing goes good and it tries to search the configuration, which is nothing but the drivers. Yeah, I forgot to inform about the drivers as well. It makes sure it tries to check a set of drivers. If this is also okay for it, I mean the blacklisted list of drivers is actually not present, it tries to resolve it to api.solarwinds.com. It also checks because in the update notification, because it's the same function. So if you check, this has to one which is to pass, not the other one, but yeah, both has the same function. So it tries to check, it resolves to the api.host, which is nothing but api.solarwinds. If this goes good, then actually the while loop, the bad stuff getting invoked, which is nothing but the crypto helper function. It wants to form the DGA, which we saw, which uses the create secure string, which goes back, not the create secure string, sorry. It tries to obtain the create, which is the crypto helper function itself, which has the decrypt short, which obtains the GUID and the DNS name, which is nothing but the decrypt short. Let's check what the decrypt short does, which makes sure it tries to have the same the domain name which is obtained of this pattern, which is matches. If yes, it has two functions which is called, which is base decode, which tries to substitute with a constant value, which is here, which has a nice kind of for each loop here to obtain the DGA. If these things goes good, the so-called result which we just found, which is the result, which has been stored in the get status, which is where the DGA has been formed, which has this constant value, which is ASVM of cold.cloud, which is the first parent domain. It tries to append with domain 2, which is nothing but AppSync, and which is domain 3, which is chooses between this EU West 1 or 2, which is where it exactly matches for us here, which is actually this is what has been matches here. Comes down, checks the status, and the HTTP helper, which is the initialize function, which is the actual backdoor being initialized. Let's go inside, which has a jobs parameter being passed, which is the it tries to declare the jobs class, which is it tries to do a lot of things: collect system description, upload system description. It writes file, which is where the the second stage payload, which is, should be a teardrop, which has been read, and run task, which it makes sure it runs in this context. And it tries to make a lot of checks. It reboots, it writes file, it deletes file, sets registry values, etc., etc. And the mission is success for the backdoor, huh? But imagine the amount of checks it really does. It's a lot. It's a lot, I would say. Pretty much it took some time for me to traverse this code to understand, to go in front and come back. But this, I think, I hope I was able to give you a clear picture